University, and currently working part-time with the Open University. So, safety in nanomaterials. How did I get into this? Well, mainly I got into this through the frustration of not being able to do all sorts of things. We were working on a variety of things that we could add to concrete to make concrete better, quicker, a variety of cheaper in some things. So we were looking at additives for concrete. We worked with grinding certain materials down. We used quite a lot of waste materials and made quite good concrete. Following on from that, the logical idea was to add some nanomaterials to it. We're working in civil engineering here, working in construction, and all our labs based around construction, people who are familiar with all the issues of construction, and our safety person went, "You have to be joking, it's the same, these things are the same shape as asbestos, I'm not having any of that in my lab." So, well, okay, so essentially you're going to have to convince me that they're safe. Well, 4 or 5 years later, I retired, having not convinced him that they were safe. Equally, he hadn't convinced me they were unsafe, nor had anyone else. But there is a great fear in the construction industry about the effects of asbestos, really because it's caused so much problem, and over such a long time scale. Many years after people have been associated with the asbestos, people have come down with asbestosis and mesothelioma in particular. And the result of that has been very, very expensive, as well as very costly in human life. But asbestos has now been taken out of lots of places. That involves a lot of cost. And therefore there's a great fear in a lot of the construction world about this. So that's sort of my background into looking into safety. And I'm now not, my computer's been causing, I'm not going and that's better. Right, finally. Now I know everyone knows what a nanomaterial is. WHO definition, the World Health Organization, materials that have at least one dimension that's smaller than 100 nanometers. There are a variety of definitions around, and I've added a little picture of some of the variety. This is the important issue that I'm trying to get across here, is that nanomaterials come in a vast variety of shapes, forms, different things within it. There was a count in, I think, the mid 2010s that came up with over 3,000 different types of nanomaterial. Now that causes problems. When we think of our sort of standard data sheets, you have a data sheet on a material, you take that material to the lab, you do everything you think of to that material, you learn a lot about that material, and then you start working with it. Whereas we're now adding hundreds, possibly thousands of different sorts of nanomaterials every year. So how is the safety industry going to keep up with that? This is looking at the EU recommendation on the definition of a nanomaterial. And I really brought this in because of the issues of how much of each material you need before you start getting worried about it. So a threshold between 1 and 50% or should we be looking at 40%, or should we be looking at 70%? Big problem with the safety is to be sure that we've got a safe material. So this is really based on looking at risks and hazards. But I want to sort of emphasize at the beginning that we need to look at the balance. So we're not just looking at what can go wrong, because of course there are masses of advantages of using nanomaterials. Sylvia, for example, mentioned some of the environmental advantages. There are advantages in terms of safety. So I'm not going to be looking at those. I'm simply looking at the hazards and risks, but please don't forget that we are looking at balance. So don't let me tip this balance too far the wrong way. The World Health Organization has come up with all sorts of guidelines. I've done quite a lot of research into this, but I haven't been able to keep up with what the WHO have done. So I've made quite a lot of use of their material, because they've synthesized material from hundreds of studies into quite a useful synthesis. So this is first looking at their guidelines on protecting workers. They make the point that toxicity depends on all sorts of things: size, shape, composition, surface characteristics, and so on, and that we like precise information. Where do we get the data from? We get the data from animal studies and in vitro, and of course there are, in some instances, some information from human studies. Not in the same way purposeful, but there's information from what has happened in certain instances. And it's worth saying at this stage that so far no long-term adverse health effects in humans have been observed. So they recommend, we've got lots of different materials, can't provide data sheets for each nanomaterial, so therefore there's a logic in classifying it. And the other thing that they're keen on looking at is exposure limits. So where do we set them? Right, part of what I'm trying to get out with this is thoughts on where we can go in the future. There is a massive amount of research that we need to do on the effects of nanomaterials, and a lot of research and production that can be done on ways of monitoring it and reducing exposure. So the WHO are currently suggesting the precautionary approach. So essentially, reduce the worker exposure, which I'm sure you're all entirely used to. So until we've got better data, we need to use the highest level of controls. Further data, therefore, may make the entire process cheaper if we can find further data that evidence the lack of problems from this. The WHO classification into a sort of, this is a classification of nanomaterials, ones that are specifically toxic, either highly toxic or have high dissolution rates. So that depends on the makeup of the nanomaterials. The respirable fibres group, with a fibre length greater than 5 micrometers, fibre diameter less than 3, and an aspect ratio greater than 3. And then the others, ones that hang around a lot, but actually aren't particularly soluble and aren't particularly toxic, which seems like a good place to start. What do they all do? Well, there are a variety of things they do to us. Organ toxicity from particular things, particularly toxins. There's a certain amount of carcinogenicity, eye damage, skin problems. And this, I've introduced this table just to show you some of the problems that we all have with determining the safety of materials. So we've got a few listed down the left here. The green bits with no in is that there's evidence that there's no harm from them. The pink bits is that there's evidence that there might be harm, and then there's a lot of no data. So we need, and this is a limited set of nanomaterials. So we need much more data before we can safely get this out into the public. Okay, then moving into, that's looking at workers. Moving on to ambient air pollution. The whole concept of looking at ambient air pollution is that people should be able to walk out of their front door and not be at risk of death from that. Now, we've improved air pollution a lot over the time since everything was steam powered and there was black smoke pouring from chimneys all over the place, but we still have problems. It's estimated that we're looking at over 4 million deaths per year from ambient air pollution and household air pollution. That's a lot of deaths. It makes it a very big factor in deaths worldwide. We can compare that with approximately 1.8 million deaths per year from water pollution. Climate change is a bit difficult to quantify, as the current estimate is something like 150,000 deaths per year, but of course this is something that's increasing year on year, and I would hope that our politicians might improve their understanding of an exponential curve before this becomes even more of a problem. And to put that in context with this, deaths from mesothelioma, which is the worst problem really from asbestos, it's a fast-acting cancer with a very poor diagnosis and generally death within 6 months or a year. But we're looking at small numbers of deaths. Nasty though. The WHO have produced global air quality guidelines. They're now looking to update them. They were produced first in the early 2000s. They're air quality guidelines for things that we can control to some extent and for things that we can measure. A lot of what we do with air quality depends on how well we can measure it. The pollutants that they're looking at updating the guidelines for, we've got things that like ozone, nitrogen dioxide, sulfur dioxide, carbon monoxide, which are well known, have health problems. We're perhaps less familiar with the bits, the particulate matter, PM 2.5, PM 10. 30 years ago or so, we were talking about PM 20. PM whatever, PMX is particulate matter, i.e. bits, not gases, where particles have an aerodynamic diameter equal to or less than X micrometers. The concept of aerodynamic diameter is that we're looking at a severe sphere of that size, which would move roughly the same way through the air. I find it easiest to think of it as falling through a sieve, which is not so far different. So we're looking at something that would fall through a sieve. So for PM 2.5, you'd be looking at a sieve with holes of 2.5 micrometers. And of course, if you think of sort of, a bit of straw, it's got a fairly small two fairly small dimensions, one long one, but it still falls through a sieve. And that's the same concept with the aerodynamic diameter. So we're looking at small particles. And a recent meta-study showed that an increased concentration of PM2.5, which we're now measuring because we can. 30 years ago, we could measure 20. Now we're down to reasonably reliable measurement of 2.5. That leads to an almost linear increase in mortality. So the more of that size particle that you have, the more deaths you have from it. PM10 seems to be a less good indicator. It's worth mentioning at the moment that nanomaterials currently are actually only a very small percentage of PM2.5. This, a large amount of it is from combustion and will continue to be so. However, nanomaterials are being sold in a greater quantity, more different things. They're going out there into the world. To start with, we're not going to see them eroding too much, but as time goes on, someone will knock some concrete over, things will erode on the, shoes will erode and the like. So more nanomaterials will come out. And if we look at the recommended targets, which is really why I wanted to look at this, there's a concept of interim targets. The idea being that you get to the final level as fast as you can, but having some measurable targets can allow people to compare with each other and the like. So they're not necessarily exactly time related. The previous target was what's now interim target 4, which was at a level of 10, which has now gone down to 5. And actually a lot of people are still at 35. This being the annual amount, and then we've got a 24-hour target as well. So the targets are getting tighter, and the controls on small materials are likely to get tighter with it. And for the first time, the WHO limits have actually talked about ultrafine particles. They considered them way back 2005 when they're first developing this, decided there wasn't enough evidence to include levels for them. They now can accept that there is evidence of there being a problem, but that it's not consistent enough to actually produce a level for it. People are measuring different things or in different ways, and therefore we haven't got the evidence for it. So they come up with a good practice statement. And this good practice statement, I think, should provide a lot of ideas for things that are really needed in terms of research. So measuring the particle number concentration for sizes of less than 10 nanometers with no restriction on the upper limit, well, that's putting a consistency into measurement, which would be useful. The next part of it is to integrate into the existing air quality monitoring stations. So suggestion we distinguish between low and high particulate number concentrations and utilize emerging science and technology to improve epidemiological studies and management. There's a lot of work to be done there. Going back to the air quality monitoring, I'm not sure how familiar everyone is with this, but we have a lot of air quality monitoring stations worldwide. They're integral to most countries' management of their air quality. They're there's enough in a lot of places that they're just all sitting on top of each other. I thought I'd bring out an example of a local town. This is Liverpool in the UK, where there are 6 local stations. So that conglomeration sort of comes out to somewhere between 6, and there's a lot more in London, for example, in some of the big cities. And each of them is going to look something like one of these. It's fairly small. One of these examples shows some of the equipment inside. But what we're looking at and what they want to do is to measure ultrafine particles all around the country, the world, in fairly small air quality monitoring stations reliably. And ideally, picking out what actual size they are, rather than just saying anything less than 10 nanometers or less than 5 nanometers. If we can separate out those, that'd be even better. There's a lot of work to be done in developing the mechanics of doing that at a reasonable price. Back through this. Just a few examples. We're not just looking at toxicity to humans, but there's toxicity to marine algae, freshwater algae, etc. I appreciate I'm running quite low on time, so I'm going to zoom through. REACH, I'm sure some of you will be familiar with, which EU regulation. And again, basics, we're looking at procedures for collecting information, and that's difficult when you've got thousands of difficult things to collect. And of course, we should be looking at labeling as well. Is the customer always aware that they're buying something that's got nanomaterials in them? Should they be? Do they need to be? Questions to be answered. Should we treat nanomaterials differently? Possibly, and that's what we need to look at and to work out. Couple of examples from the literature. This was one that examined the effects of carbon nanotubes on mice, and they found that essentially mice developed in a similar way when you gave them either CNTs or asbestos. There's the development of particularly, again, mesothelioma. But of course, mice aren't humans, and they weren't providing a few to be inhaled. They were giving them in large doses to the mice. We do know that biopersistent fibres can cause mesothelioma in particular. So the biopersistence is important. This study also looked at the fact that most nanomaterials are more soluble than asbestos and are therefore thought to pose little health risk. And this is quite an interesting one where they were looking at whether there are any other things to consider other than size, shape, biopersistence. And this looked at the potential for fibres which buckle, i.e. they've got a smaller bending stiffness. They're likely to lose the high aspect ratio and inside the lungs to buckle and end up as being a sort of sphere of fibres rather than lots of long thin ones. And there's lots further to research in this. Is this actually what's happening? And if so, it's actually quite an important difference between a lot of materials and the asbestos. So a suggestion of opportunities for us, classification, how much fibres are going to be a problem, the influence of bending stiffness, lots of studies, computer modelling, epidemiological studies. develop some kit that will go into the air quality monitoring stations, and your own ideas. So on that note, realizing the time's moving on, I'll finish.